All right, good morning, Transitional Algebra 2 students at CCTI. Mr. Prashar here once again. It is also looking out the window, another cloudy, dismal looking type day. The sun was out a little bit in between, which was nice. I went out for a walk this morning. Looks kind of crappy out there at the moment, but hopefully it's just another passing shower. I did send you the email today about your new assignment, which will be due next week. And if you read the email, you've also seen in there I included some things about the weather. As you know, in the classroom, I always like to talk to you guys about the weather. If you remember at one time I told you I was split on either going to school to study to be a math teacher, get my degree in math, or to get my degree in meteorology. And maybe someday I will go back and get my degree in meteorology, but I do like to follow the weather, and as of now, some of the models are hinting towards some very summer-like weather beginning to take place this weekend coming up, and then Monday the 18th, maybe perhaps low 80s, dare I say. So that may be something for us to look forward to as we head forward. Also look forward to, we're well under a month to go of school. I think you guys have been handling this okay. I miss you guys, I really do. I miss all my students, even the ones that give me a headache. But seriously, I do miss having everybody in class. I don't enjoy this particularly teaching at home by myself here. No one to talk to other than myself. But I hope you guys are managing, and I'm hoping that we'll be able to be in the classroom before we know it. Hopefully next year's school year starts off that way. Last week we looked at the imaginary numbers, so we finally got an answer to something like this. The square root of -1 we call I, right? And we saw this theorem that says, well, if we have the square root of -k, that means we have I root k, right? So, for example, square root of 9, we could write that as I root 9, and then we know that the square root of 9 is 3, so we call this 3i. We also saw how this helps us solve equations. For example, x squared equals -1 does not have a number solution in the reals, but now because of the imaginary numbers, x is plus or minus I. So we have two solutions, minus I and plus I. So thank you to the imaginary numbers. Thank you, Gauss, one of the mathematicians that helped put these in place. But today's lesson is on what we call the complex numbers. So what we're going to do today is see that numbers like I and 3i and minus I, they belong to an even bigger set of numbers, and we call those the complex numbers. So let me draw you a diagram here. Maybe this will help you to kind of understand what I'm talking about. I'm just going to be as brief as I could so you can understand. For example, the complex numbers think of all the complex numbers as being in this box. So the complex numbers are made up of, on one half, the real numbers, which is interesting. So things like 0 and -1 and 2 and pi and the square root of 7, those are actually considered complex. You never knew that, but I always kind of hinted that towards you in class a little bit, that all the real numbers are actually belonging to this bigger set called the complex numbers, which we usually denote by a scripted capital C. Now, what else do the complex numbers have? Well, they have the imaginary numbers, right? So things like 2i and minus I, and things like 7i. But also something of this form, something like 2 plus 3i, or -7 minus 4i. These would be considered complex numbers. So what belongs in here are things that take the form of a plus bi, where a is a real number and b is a real number and I is the imaginary number. We call this the real part, and we call this the imaginary part. So not to get too technical, but in this set complex, if you're a real number, that means you look like a plus 0i. Because real numbers don't have this imaginary unit attached to it. There'll just be the letter a representing a real number. But you can also be an imaginary number, right? Where a could be 0. So you could have something like 0 plus bi, and that would be an imaginary number. Or as mathematicians would say, a pure imaginary number. So the best way to think of this as everything you learned to this point now, from grade school to now, is considered actually a complex number. Real numbers are part of this bigger set C. And the complex numbers contain strict imaginary numbers like 2i, minus I, and 7i, but they also contain numbers like 2 plus 3i, minus 7, minus 4i, because they take this form a plus bi. So if someone on the street asked you what is a complex number, you would tell them it's anything that takes the form a plus bi, and that would be enough, and they should understand. Okay? So that's a brief introduction to the complex numbers. As like everything else I've taught you in mathematics here, you could spend years just on this topic, right? In college, you study calculus, and there's a course in college that we call complex analysis, which is taking everything you've done in calculus with the real numbers, things in the form a plus 0i, and you expand that to the imaginary numbers, a plus bi, where we have some imaginary unit. So, again, by the way, the sun's out now, that's nice. So this is what we're going to be talking about. Now, of course, we're not going to get technical on the theory of this. All I'm going to show you today is how do we perform operations with complex numbers, which is not too painful because, for the most part, complex numbers, a plus bi, they follow all the patterns that the real numbers do. So we could add, subtract, multiply, divide. Dividing is a little bit different, I'll show you. We could distribute, we could factor, we could do all that stuff, right? You guys love factoring, right? We could do all that over the complex numbers, and that's what I'm going to show you in the next set of examples here. And again, I have this in the lecture notes, and in the email I sent you this morning, you'll also see that it's important to read the textbook because they give you some good information, and the textbook actually shows you how complex numbers are related to electricity. And they give you a very nice diagram, better than the diagram that I drew you on the board here, a very nice diagram on how complex numbers are arranged. So please make sure you read that. So I'm going to show you first how to add and subtract. And you'll be pleasantly surprised how easy this is. So let me give you an example. Say we want to add 3 plus 4i, and we want to add 7 plus 8i. So typically this is the way you'll see it in any standard math textbook. They put the plus in the middle and they use parentheses around each item. This thing is actually just one number. This thing is one number even though it looks like it's two. Because remember, all complex numbers take the form a plus bi, okay? Let's see who's that. Oh, my buddy Ronnie Harkins. Okay, so what we're going to do is to add complex numbers, you just combine like terms. So the first step is drop the parentheses. So I'm going to write this as 3 plus 4i plus 7 plus 8i. Just like that. We put the numbers with the numbers and the i's with the i's. So you have 3 and 7, those are the real parts. That gives you 10 plus you have 4i and 8i. Those are your imaginary parts. 4i and 8i is 12i. So your final answer is 10 plus 12i. And that's how you add complex numbers. Typically, we always write it in that order. Now, if you wrote it as 12i plus 10, am I going to mark that wrong? Of course not. But it goes against convention. Usually you write it with the real part in the front and the imaginary part in the behind, okay? So all this is a like terms game. Let's look at subtraction, because subtraction kind of follows what you've seen before as well. We'll stick with the same example, but slap a minus in between. So 3 plus 4i minus 7 plus 8i, like that. So what you want to do here is, again, drop the parentheses, but you also want to make sure you change signs in the second parenthesis because you have a minus floating in the front. So it's going to be 3 plus 4i minus 7 minus 8i. So you see, I dropped the parentheses but changed the signs on these guys here. Collect like terms. 3 minus 7 is negative 4. 4i minus 8i is minus 4i. Hence your final answer is negative 4 minus 4i. Again, all we're doing is just combining like terms. That's all there is to it. That's all there is to it. And again, this whole thing is one number. This is one number. It's just written that way because it's a complex number. Okay? So that's how you add or subtract. Now, let's look at multiplication. So multiplication behaves for the most part the same way it does in regular real number multiplication. So here's an example here. Say we have 2i times 8 plus 5i. So that you distribute like you normally do. 2i times 8 would be 16i. And then 2i times 5i, remember, this is going to be 10i squared. Because remember, I times I is I squared. Now the only catch you got to remember, people, is the fact that whenever you see that I squared, do you remember what that becomes? Do you remember what you write in place of it? Yes, no, maybe, who knows? It's negative 1. So this is going to be 16i plus 10 times negative 1. Anytime you see I squared, it becomes a negative 1. So we have 16i minus 10. Now, you could write it that way, or you could write it conventionally as negative 10 plus 16i, because typically we put the real part in the front and the imaginary part on the hind end of the expression. So negative 10 plus 16i. Okay? So that's multiplying. That's not too bad. Well, if we look at another distribution like that. Okay, how about something like this? Let's do negative 4i times 7 plus 6i. How about that? So again, we're going to distribute. Yeah, negative 4i times 7, that's negative 28i. Negative 4i times a positive 6i, that's minus 24i squared. Remember, I times I is I times I is I squared. So we have negative 28i minus 24 times. Now remember, I squared, once again, is that minus 1, right? So we have negative 28i minus 24 times a negative 1. So we have negative 28i plus 24. Because negative 24 times negative 1, positive 24. And then, again, because I want to be a good mathematician, I'll write it in proper form as 24 minus 28i. 24 minus 28i. And you got it. Okay, again, real part out in front, imaginary part in the hind end. So this might be a good place to pause this video if you want to go back and practice adding and subtracting and then multiplication with distribution. The next part I'm going to show you is how do we FOIL, your classic foiling technique in terms of multiplying complex numbers. So I'll give you a moment if you want to go back and redo these, and we'll pick back up with that. This is the road, this is the road, sitting out once more, all out the veil rising. Okay. Okay, next up is the FOIL technique. So this will be number 3. something like 4 plus 3i times 4 plus 2i. Right, so let's do this. And just by looking at this, this is your classic FOIL game, right? You're so used to doing this, you could do it in your sleep by now. So you do 4 times 4, which is 16. 4 times 2i, that's plus 8i. 3i times 4, that's 12i. And 3i times 2i, that's plus 6i squared. Right? So we got that. And now we have to combine like terms. So in the middle you have these i's. An 8i and a 12i gives you a 20i. So you got 16 plus 20i plus 6 times -1. Remember, once again you have that I squared. This is going to happen all the time pretty much. You have the I squared, that becomes a -1. Okay? So you have 16 plus 20i minus 6. Put the real parts. You have 16 minus 6, which is 10. So you have 10 plus 20i. And that will do it for you. Again, we're just putting the like terms together. So again, nothing to get in a twist over. Classic FOIL, combine like terms, easy peasy, Japanesey. Okay, let's look at 2 more examples here. How about this guy? Let's do 8 minus 3i times 4 plus 5i. Now you could probably do this without me here. 8 times 4 is 32. 8 times 5i, that's plus 40i. Negative 3i times 4 is minus 12i. And negative 3i times 5i is negative 15i squared. Okay, once again, combine like terms. You got 40i minus 12i. How much does that give you? What is that going to be? 28. So plus 28i minus 15 times -1. Okay? So what we got here is 32 plus 28i plus 15. Put the real parts together. The 32 and the positive 15, they go together, of course. That's going to give you, looks like 47 plus a 28i. Again, I think it's easy, right? You should too. Classic FOIL. You're in like Flynn, right? That's a good movie, by the way, too. That's a little bit ahead of your time, in like Flint, but you can look that one up. And I'm going to show you one more example where something interesting happens here. Again, a piece of chalk. Now, we've seen every time we've done this FOIL, we get a complex number back in the proper form, a plus bi. But isn't there going to be a time maybe that you would probably think that you're not always going to get an answer that looks like this, you know, and I'm going to give you one such example here. How about this one? This will be example 5. 2 plus 3i times 2 minus 3i. If you look at this thing, this should take you back to thinking of real numbers and x variable in the reals. That when you have the same stuff in the parentheses, but just an alternating sign in between, you get a different answer. Something usually cancels out. And it should be no surprise here, in the complex case, the same thing does happen, as you're going to see. So 2 times 2 gives you the 4. 2 times negative 3i is minus 6i. 3i times 2 is positive 6i. And 3i times negative 3i is minus 9i squared. So the FOIL, the multiplication works like normal, but right away, you see what happens here. The middle terms are gone because they're opposites. So we're left with 4 minus 9i squared. And once again, you have the I squared, so that stands for negative 1. So you have 4 minus 9 times negative 1. That leaves us with 4 plus 9. And look at this. How do you get this? Look at it. It's just a real number. It's 13. So what happens here is if you multiply by what we call conjugates, the conjugate of 2 plus 3i is 2 minus 3i. And that term conjugate is going to be coming up here in the next segment. If you multiply by the conjugate, you get a real number back. Now remember, 13 is a real number, but 13 is also a complex number, because if you're a real number, you're automatically complex, as I told you earlier, because you could write 13 as 13 plus 0i. So that's why if you're real, you could be complex, because you just write 0 for the imaginary part. But isn't that kind of cool? So if you see this happening, you're going to have no I left in your answer. So just keep that in mind, okay? So this might be another good place for you to pause now that you know how to FOIL with these complex expressions. And all I have is one more type of thing to show you in this video, and that's how we divide. Now the directions aren't going to say divide, they're going to say something like write in the form a plus bi. But that's your cue to do what I'm going to tell you next. So why don't you go back, try these problems, and I'll come back and show you the last types of things we have to do. Okay, so here we go. I'm going to show you how we divide, essentially. So there's something called conjugates. Conjugates. So for example, if I give you the expression 5 plus 2i, its conjugate is its partner with the different middle sign. So partner or conjugate is 5 minus 2i. If we had 5 minus 2i, its conjugate would be 5 plus 2i. So you keep all of the stuff the same, you just change the sign that joins them in the middle. That's what we call a conjugate. Now, that's going to be very important for the next example I'm going to show you here. How do we go ahead and combine a fraction to get us to drop out the bottom. So here's an example. So we want to write in the form a plus bi. So that's our goal, to write it as a plus bi. And this will be 3 minus 4i divided by 2 plus 5i. Here's your example, okay? So we have 3 minus 4i divided by 2 plus 5i. What we got to do is divide this, and we want it to get it to look like a plus bi at the end. It doesn't look like that now because there's too many numbers and too many i's floating around. Here's how you do it. You go right to the bottom, the denominator. You see in the bottom you have 2 plus 5i. We want to multiply the top and bottom by its conjugate. So the conjugate of 2 plus 5i is 2 minus 5i. So we're going to multiply top and bottom by 2 minus 5i. And you know why we can do that? Because we've seen this trick before. It's not witchcraft, it's just mathematics. If you multiply by the same thing, this is multiplying by 1. You can multiply any damn number you want by 1. It doesn't change the identity, right? It's 2 times 1 is 2. Negative 2 times 1 is negative 2. This being multiplied by the conjugate doesn't change it, but it allows us to work the problem in the way we need it to. So now, what do we have here? We have 3 minus 4i times 2 minus 5i over 2 plus 5i times 2 minus 5i. So you see that? So we're going to do classic FOIL. So up on the top part, you're going to have 6 minus 15i minus 8i plus 20i squared. And on the bottom, you're going to have 4, and I'm just going to jump right to it. It's going to be 4 minus 25i squared, because they're the same things except the alternating signs. That means the whole middle, we don't even care about the middle, because the middle cancels out. Poof, gone. Right? Up in smoke. So, all we got to do is simplify this down. Up on the top here, you're going to have 6 minus 15i minus 8i. So that's going to be 6 minus 23i minus 20. See where the minus 20 is coming from, because this is 20 times negative 1 because of the I squared. And in the bottom, we're going to have 4 plus 25. This becomes 25 because this is going to be negative 25 times a negative 1. So that's what we get there. So now what we're going to have here is, it looks like a negative 14 minus 23i over 29. Okay, so if you have negative 14 minus 23i over 29, you're practically done. We just have to write this as two separate fractions. So we're going to write this as negative 14 over 29 minus 23i over 29. And that will be your final answer. So all we do is we split up the fraction there into its two pieces. And that's the a plus bi form that we need. So you see, this problem is a combination of all the things you learned in Algebra 1 and in algebra in general, plus adding the fact of the complex number idea. Okay? So we multiplied by the conjugate, did classic FOIL, simplified likewise, and then separated it so it was in the form a plus bi. So there you have it. Okay? So that's how you do such a thing like that. I think it'd be good to do another example. So I'll do one more example with you here, and we'll end it there. My stomach is rumbling, so it tells me we're getting close to lunch. I have, what do I have today? I have half of a wrap left from the Freeland Diner. Very good. If you're ever traveling through Freeland, Pennsylvania, please stop in to see Don and Tony and Chris and Billy and Kojak and the wonderful staff at Freeland Diner. You won't regret it. It's excellent food. They are open, let's see, Sunday, Monday, and Tuesday they're open until 3, and then Wednesday to Saturday they are open until 8:30. For takeout only as of now, but once the restrictions get loosened up, you'll be able to sit in there once again. Okay, last example. 7 plus 4i divided by 3 minus 5i. And we're going to once again do the same thing. We're going to go ahead and get this to look like a plus bi in the end. So that means we're going to multiply top and bottom by the conjugate of the guy in the bottom. So if we have 3 minus 5i, the conjugate is going to be 3 plus 5i. So there you have it. Okay? So we're going to have 7 plus 4i times 3 plus 5i over 3 minus 5i times 3 plus 5i, right? So, what we're going to get looks like 21 plus 35i plus 12i plus 20i squared over 9, and this is going to be minus 25i squared. Once again, skipping the middle part because they're going to cancel out. They're going to cancel out for each other because they're the conjugates. So what do we got here? Well, it looks like we'll have 21 plus 47i minus 20 over 9 plus 25. And that's going to give us a 1 plus 47i over 34. And then we can write that as 1 over 34 plus 47 over 34i. See how fast I went through it? That's how fast I'll be able to do this as well. Because it's all skills that you've learned from the past. So with that being said, guys, I hope this helps you out with your work. It's 1 to 19 in the textbook, not too hard. You'll be doing this kind of game and the other games we played here. With that being said, enjoy the rest of your day. If you have any questions, please feel free to call or text, email, whatever you need to do. I'll be willing to help you. Hang in there, we're almost done. This is one of the last topics we're going to be doing. We don't have too much more to go in the Transitional Algebra 2 course. So until next time, Mr. Prashar here once again. Enjoy the rest of your day, enjoy the rest of your week, and I'll see you when I see you.